Good morning, everybody. I am Gabriele Pisano from the Institute of Construction Technologies, and this is a joint work with Antonio Bonatti and Professor Gianni Roia Cafagni from the University of Parma. I will talk about a statistical model, micromechanically motivated, for assessing the risk of spontaneous breakage in glass, and able to quantitatively evaluate the effectiveness of the heat shock test based on the time of the heat shock test. So everybody of us knows that tensile strength of glass is governed by surface microcracks, which open almost exclusively in mode 1. This is why only the component of stress orthogonal to the crack axis is responsible for failure. That is why a dependence upon the state of stress arises. And then because of the probabilistic nature of crack sizes, a size effect characterizes glass strength. Another peculiar aspect for glass is subcritical crack growth, because of which cracks can grow over time, even for stress level much lower than the critical one. This is why the more common way for strengthening glass is to make the tempering process, according to which the glass is heated up to 650 degrees and then rapidly cool, generating tensile residual stresses in the core part of the plate and compressive stresses in the other layer. That is why cracks can grow only when tensile stresses generated by external action overcome the compressive residual stresses. But the main drawback of the tempering process is the probability of having failure because of nickel sulfide inclusion, which is a mineral. Nickel sulfide is a mineral contaminating the glass melt during manufacturing. It has two phases of relevance: alpha, that is stable at 379 degrees, and the beta, that is stable at room temperature. But the cooling is so rapid that there is no time for transformation, and that is why the inclusion are in the metastable alpha condition, and they transform in time. But the transformation, the phase transformation, is accompanied by a volume expansion, because of which the surrounding glass can be stressed and crack can initiate if the inclusion is in the core part of the element when the tensile stresses are tensile. Despite all mitigating measures that industry has adopted, today it's not possible to totally eliminate the presence of nickel sulfide in glass. That is why most standards prescribe the heat shock test, that is a thermal process which has the main aim of speeding up the alpha-beta transformation, so to have the rupture of critical elements during the test. But in the standards we have variability, a very high variability of the time of the heat shock test, bypassing from 2 hours for the EN 14179 to 8 hours for the German DIN. So what is the probability of spontaneous collapse of a glass plate, and how the heat shock test can affect such probability is still a matter of debate. So this statistical model must be considered a starting point to solve these problems. The hypotheses underlying the model are that the distribution of residual stresses is parabolic. Okay, this is a generally accepted principle. The volume is ideally divided into representative volume elements, whose main characteristic is that they can host only one inclusion, and that they are characterized by a certain probability of hosting an inclusion. A weakest link in the chain approach is used because obviously the reaching of the critical condition in only one nickel sulfide inclusion leads to the collapse of the whole element. A Pareto distribution is used to interpret the variability of inclusion sizes. This seems reasonable because the smaller is the inclusion, the higher is the probability of finding a bigger inclusion. But at the same time, we have a not negligible probability to find an inclusion that is several times bigger than the bulk of the distribution. In fact, we can look at the power law distribution, the Pareto distribution has a very heavy right tail. then, to be on the safe side, we have assumed that the initiated crack from the inclusion is always orthogonal to the direction of maximal principal tensile stress. And finally, the correlation between the inclusion size and the critical stress is given by a micromechanical model proposed by Swain in 1981. Obviously, the composition of the inclusion is extremely variable. We can classify the inclusion on basis of the chemical composition in near, over, and strongly over-stoichiometric. But the strongly over-stoichiometric that are quite rare can be considered not critical because their transformation lasts more than the lifetime of the element. That is why they become not critical. And this is why we here neglect the presence of strongly over-stoichiometric inclusion. The difference between the main difference from the mechanical point of view from the near and the over-stoichiometric inclusion is that the transformation is very rapid for near stoichiometric inclusion of the order of 10-20 minutes for the time of the Itzhak test, while it is much slower for over-stoichiometric inclusion. So the distribution of the over-stoichiometric inclusion will be subject to a right truncation by the Itzhak test. And the longer is the Itzhak test, the stronger is the right truncation, because obviously the bigger inclusion that are in the core part of the plate will lead to failure during the Itzhak test, and while the smaller inclusion will remain inside the glass plate, and the longer is the Itzhak test, the smaller is the inclusion that became critical. So I do not dwell on the analytical manipulation of the model here because I have no time. There is no time for this. What we have found are three statistical models. The first one that can be used for plates not subjected to Itzhak test. And here we have a formula a la Weibull, or the two-parameter type, in which 3 on 2 alpha star is the shape parameter, eta LT is the scale parameter, V is the volume, so it is evident the dependence upon the volume and the volume size effect in this model. Here we have a model for the short Itzhak test. We consider a Itzhak test short when it lasts enough to have the full transformation of near stoichiometric inclusion, but at the same time, the over stoichiometric inclusion are only partially transformed and are not still in contact with the surrounding glass. This is why here we have PSV, that is the probability of survival of elements which contain fully transformed near stoichiometric inclusion. This is not equal to 1, because a fully transformed inclusion might not lead to failure during the Itzhak test, but during the lifetime because of the subcritical crack growth of interior cracks. While the exponential terms refers to the over-stoichiometric distribution, which is not truncated because for short Itzhak tests, they are not in contact for glass. And then we have the formula for long Itzhak tests, in which even the distribution of over-stoichiometric inclusion is truncated, and the Upsilon Itzhak test brings the dependence upon the time of the Itzhak test. So for what is of interest is to notice is that all the parameters of these distributions depends upon the parameters of the Pareto distributions for the inclusion sizes. And then the parameter of the Pareto distribution can be graphically estimated through by analyzing a sample of nice inclusion measurements. So we don't need destructive tests to define the failure probability, the spontaneous failure probability. Here, just for illustration, I show how the failure probability can vary during the time of the Itzhak test. For a time t equal to 0, we use the formula for no Itzhak test. For a short Itzhak test, the formula that obviously is related to short Itzhak test of the order of 10, 15, or 20 minutes. And then the failure probability decreases with time with the time of the heat-shock test according to the formula for long heat-shock test. You can notice that after the first red point, we have a horizontal line. Here we have that the near stoichiometric inclusion are fully transformed, but while the over-stoichiometric inclusion are partially transformed, not still in contact with glass. That is why here the failure probability is constant and then decreases. The failure probability does not tend to zero, even for very long heat-shock tests, because here we have that fully transformed over or near stoichiometric inclusion can lead to failure because of subcritical crack growth. Obviously, subcritical crack growth for interior cracks is still an open issue. We can think that it is much slower and much limited, more limited than for surface cracks, since there is a very small contact of water, almost null. And so it is so important to define, to precisely define what is the subcritical crack growth for interior cracks. Obviously, the higher is the effect of subcritical crack growth, the higher is this volume, this value of failure probability, and vice versa. Unfortunately, the data present in literature are only fragmented and partial, so we are trying to use the data that we have found in literature to show the potentialities of the model and to make a parametric analysis to find reliable values for the parameters governing the model. Here we refer to the study recently published by Casper, and this V0 is the volume that statistically contains on average only one inclusion. It's 0.6 meter up to 3. Then we have calibrated the parameter of the Pareto distribution for inclusion sizes by using the measurement here recorded that are published in a recent paper by Casper and collaborators, even though these measurements refer to green glass and not to transparent glass. Then we have assumed that the percentage of over-stoichiometric inclusion is 33%, and that near and over-stoichiometric inclusion have the same shape parameters. And we have recalibrated the parameters for the distribution on over and near stoichiometric inclusion accordingly. So for what concerns the volume size effect of the model, is such that if we compare pane of thickness H and area A with two panes of thickness H and area A on 2, the survival probability of this pane is exactly equal to the probability that none of the two smaller panes fails. And the same is true for the thickness. So if we compare a pane of thickness H with two panes of thickness H on 2, the survival probability of the thicker plate is exactly equal to the probability that none of the two smaller plates fail. Here I have defined a reference glass pane, 2 meters per 1 meter per 4 millimeters, and I plotted the probability of failure for elements that are not subject to heat-shock test, how vary with the ratio between the volume and the reference volume. Here it is evident that the model is strongly affected by the value of the stress intensity factor to be considered critical for rupture in the long term, and this depends upon the subcritical crack growth, obviously. But then we came back on this point. Here I plotted the failure probability with the time of the heat-shock test for different values of the maximum volume expansion for the phase transfer, for the alpha-beta phase transformation. If we observe the graph on the right, in which NB is the expected number of elements for having one breakage, we can notice that by using a value of 4%, in literature we can find the values of the maximum volume expansion between 2 and 4%. For 4%, probably the number of expected elements for having only one breakage is too small. This is why we think that the most reliable values are between 2 and 2.5% by comparing with the results of practical application. For what concerns subcritical crack growth, it is of importance to recall that for surface crack, the threshold activation limit is 0.3 megapascal per meter up to 0.5. But if we consider low values of KLT of the order of 0.4, so we have that the effectiveness of the heat-soak test is totally null. That obviously is in contrast with the practice. This is why we think that the most reliable value for stress intensity factor to be considered critical for having breakage in the long term is between 0.6 and 0.7. This must not be striking, that is close to the fracture toughness for glass, that is 0.75, because this is subcritical crack growth for interior cracks, not for surface cracks, in which water is not present, and then so we can expect that the subcritical crack growth is much more limited than for surface cracks. I try to vary the percentage of over-stoichiometric inclusion. This coefficient influence only when the model, only when the inclusion are partially transformed. But if we consider low values of this parameter, they are probably the only one of importance if we refer to the study by USV. The variations in the model are extremely moderate. So this parameter is certainly important to correctly calibrate this parameter, but probably is not so crucial. And finally, I analyzed the sensitivity to V0, that is the volume that on average contain one inclusion. The model is strongly affected by this parameter, as you can see from the graphs. And this means that it would be very important to make an ordinate collection of the existing data to accurately define the value of V0 and consequently to precisely calibrating the parameters of the Pareto distribution for inclusion sizes that are at the basis of the model. So finally, here I have presented a statistical model which must be considered a starting point for solving the long-standing problem of defining what is the risk of spontaneous breakage in glass and to quantitatively evaluate the effectiveness of the heat-soak test on basis of the Feiler probability depending upon the time of the heat-soak test. Obviously, much research is still needed. Here are summarized what are the points that need research. An organized collection of the existing data would be ideal to correctly define the volume V0 and the parameter for the Pareto distribution, to make investigation on the volume expansion consequent to the complete alpha-beta phase transformation, the choice of the composition to be considered of reference for over-stoichiometric inclusion, because the time obviously is strongly related to the composition that are considered of reference. And from the fracture mechanics side, it would be developed a more refined model if construct a micromechanical model to interpret the crack initiation, not only by considering the inclusion side, but even the tensile stress. And at the same time, to find, it would be so important to find an analytical model that is able to interpret the subcritical crack growth for interior cracks and not only for surface crack, to define in accurate way the value of the stress intensity factor to be considered critical for breakage in long term. So, for conclusions, a micromechanically motivated model is proposed for solving the long-standing problem of defining the risk of spontaneous breakage in glass due to nickel sulfide inclusions through functions that are of the Weibull type. The statistical model here presented can characterize the probability of failure for glass plate subject to shortened heat-soak test, and through this model we can quantitatively estimate the effectiveness of the heat-soak test. A sensitivity analysis has been performed to individuate reliable values for the parameters governing the model and to point out what are the aspects that still need research. But maybe what is the most important point to highlight is that this model would allow to calibrate the holding time of the heat-soak test on the basis of the risk reputed acceptable for a specific glass element, and hence different holding times of the Hitchcock test might be defined for elements in different classes of consequences. Thanks for your attention.
Thank you thank you very much, Gabriele Pisano.
Thank you.
Now we have time for questions. Do we have any questions from the audience? Please, I'll need the microphone.
I have a question about the time. Did you consider that the Hitchcock test also has a heating up period? Or do you only think of it to be isothermal?
No, here I'm just considering I'm not considering the heating time of the Hitchcock test, only the time in which the temperature is at the correct temperature. So it's a statistical model that not enter inside the technological aspect of the Hitchcock test.
Okay, thank you.
Okay.
Any more questions?
Just one.
Can you hear me?
Yeah.
Have you considered the logarithmic normal distribution instead of the two-parameter Weibull distribution?
Okay, no, because the distribution has been constructed by a macro approach. So the two-parameter Weibull distribution is what is the results of the analytical manipulation distribution a la Weibull, or the Weibull type. So I should change the hypothesis underlying the model to find another distribution. Unfortunately, in 20 minutes, I had no time to show the analytical manipulations. So I just listed the hypothesis and show you the results.
Great, thank you.
Okay.
Okay. But I'm wondering if, according to your model, is it possible to determine somehow an optimal duration for the Hitchcock test? Because it seems that after at a given time, the gain is very limited.
Yeah, the idea, if I come back to the one of this, the idea is that if I define that for a certain element, a specific element, I need a specific Fowler probability that I consider acceptable, I can decide what is the time of the Hitchcock test that allow me to reach that Fowler probability. That is why I can think to differentiate the Hitchcock test for the practical use of the element that I subject into the Hitchcock test. So this is the idea. Okay.
Very good. Thank you for the questions. Any other questions still in the audience? If not, then we give a big hand again to Gabriele Pisano.
Thank you.
Hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao.